When we left off in the last video, we were talking about checking the assumptions for a simple linear regression. We said that the first three were basically the same as in a correlation, and we were talking about the homogeneity of variance assumption when it was run out of time, so I kind of rushed. But to go back and say something about that, what we're looking out for is fanning, and this is a scenario where at one end of the independent variable, all the points are very close together. The observations are tightly packed, so there's very little variance or residuals. Over here on the other end, you would see a lot of variation. And the problem with this is that you can plot your regression line. Imagine that's the regression line. And at one end, your predictions are going to be really accurate. So I think that the horsepower will be 7.362, and it's like super close to that. On the other end, I think the horsepower will be 7. And then now some of them are way over, some of them are way under, and when you go through, if you don't pay attention to this assumption and you ignore that, then when you get to the end, you're going to act like you have a reasonable regression line, a reasonable model, when in fact it's highly inaccurate at one end. So you want to be really aware of that. Okay. Anyway, the last assumption is normally distributed residuals. So we're using variance and residuals are kind of the same thing. So this is how they're spread out. This one is going to be the distribution of those, and you actually have to run the analysis in order to check for this. So we're going to have to go back to it. So we'll go through the whole analysis. I'll show you. I'll point out the point where we make that happen, so we can test it, and then we'll go from there. Okay, how to do this. So in this instance, I'm going to walk through it in the PowerPoint view instead of going into the actual SPSS, and you can see what we're doing here. I might make another video actually walking through it. We'll see if we do that or not. Okay, so to run the regression analysis, so we have our data set open. So this is a data set with a bunch of different car variables, different things about the cars. It's analyze, and then regression. So last time we had correlate, now we're to regression. And we want a linear regression. So you can see that there's different kinds of regression. We're always going to be using linear regression in this class. So of any regressions, we're never going to use any of these guys. Okay, so you click on that. It's going to open up a dialog box that looks like this, and you're going to select your independent and dependent variables. So hopefully you have those straight by now. So independent variable predicts the dependent variable, or the dependent variable depends on the independent variable. This will be your x-axis, your y-axis. So we're going to use engine size to predict horsepower. Notice there are extra variables. Don't let that freak you out. You're only going to pick the ones that you actually need. So don't pick all of them. That would be unnecessary. So you're just going to pick the ones you need. And then after you do that, you're going to hit the save button. And the save button, it gives you options of all the different, this actually comes up, all the different things you can save. These actually would all become new variables. So you see the term residuals here. That should ring a bell. We've been using that term this whole time. And there's different ways of representing the residuals. And we're going to choose unstandardized because it's the most intuitive. So the unstandardized residual is the distance from the regression line to our which is our predicted value, to the actual value in the original units. So it's pretty easy to understand. So you'll click unstandardized, and then when we're done, if you go to your variable view, there's going to be a whole new variable at the bottom. I'll show you that. That is that unstandardized residual, and that's what we're going to use to test that last assumption, but we'll get there in due time. So you did that, and so you would click I think down here you actually can't see it, but it says OK. And then you click OK here, and then it's going to run, and you'll get 5 tables that pop up in your output. And some of these might look a little familiar. You've seen some of these terms before. So this is just telling us what our variables are. Dependent variables, horsepower. Engine size was the independent. Like I said, later on we'll have more than one independent variable, and so you'd see more in that box right there. Okay, here we have the summary. So we have the R and the R squared. So the R is really just our correlation coefficient. The R squared is R squared, which is the coefficient of determination. Down here we have an ANOVA table. And you might think, wait, ANOVA, I remember that from the other class. Yeah, exactly. These are actually mathematically pretty much the same processes, but they're approached from a different orientation. ANOVA is usually used when it's an experiment, and regression is normally used when it's a correlation study. Okay, but you remember before, if there was an overall effect, we would get a significant F statistic, and that's similar to what's going on here. I think later in the PowerPoint it goes into more detail there. We get our coefficients, which is what we use to create our equation, to actually create our model, our statistical model. So we'll be using this information. And down here, this has to do with the residuals that we created. So we made that new variable. Okay, so the last assumption was normally distributed residuals. So we'll go back and check that assumption before we go forward and interpret the rest of the results. So here's the new variable it created. So this is in variable view, and here's all the different variables, all the different things to do with the car, miles per gallon, how long the car is, and how much it costs. And then here it's res_1, which is under standardized residual. You can change, did I do that? I did it. You can change the name of this if you want to, keep track of it later. I don't know if you really need to, but you can change the name of that. And we're going to check to see if they're normally distributed. So the assumption is normally distributed residuals. So just like we checked to see if the other variables were normal, we want the residuals to be normal. So we're going to create a histogram. So it's the chart builder thing we always use. And the very last variable is unstandardized residuals, which bring it down here on the x-axis. There's no y variable. And then it creates our histogram. So again, we're looking to see that they're roughly normally distributed. Again, residuals are the distance, and they're unstandardized, so the raw distance from the regression line, or prediction, to the actual value. So what this means, this value right here that's 100, that means that for one car, we underestimated the horsepower by 100. Over here, we overestimated the horsepower by 55. So there's a difference between what we're guessing and what actually happens, and we want this to be as small as possible. But they're normally distributed, so we say, hooray, the assumption is met. Life is good. Okay, so we're going to focus on these three middle tables when we're interpreting the results. This one just lets us know we entered the variables, right? This one has to do with the residuals, and all we cared about was what we just did right here. So we're going to ignore this from now on. And we're going to look at these three tables. So we'll go into detail. You can understand exactly what these mean. So the first table is model summary. So basically you interpret this just like a correlation table, just the same. So in a simple linear model, a simple linear again means there's one predictor variable. It basically is exactly like a correlation. So this is the correlation coefficient, 0.82, we're rounding that to the hundredths place. And then this is the coefficient of determination, so the r squared, and this means that the model explains about 66% of the variation in horsepower. And you might think, well, you mean that engine size does? Yes, because in this case, that's the only predictor. But later, we could have more predictors, and then it's going to say, okay, taking all of that information together, it predicts a certain amount of the variance in the dependent variable. Okay, let's see here. So now this is our next table. So we had this one, and now we'll go to our ANOVA table. And this gives us a test of the fit of the overall model. Okay, so basically this is asking, does our overall model give us a significantly better prediction than just using the mean? Right? So if the significance of the F ratio is less than 0.05, so our same criteria, we can say that this model results in a significantly better prediction of horsepower than using the mean. So overall, this basically means the regression model predicts the horsepower significantly well. It's worth using the model, basically. Okay. And then lastly, we have our coefficient table, and this is the most interesting part, because this gives us detailed information about each predictor in the model. Again, since it's simple linear regression, there's only one predictor. It also gives us information to actually use the model. So we create the model, and we can use it to make predictions. So I'll show you how that works. So the constant is 53.21. And then the engine size, our predictor, is 42.99. And we'll go over here and look at the significance level. So we don't look at this really for the constant, but we do for the predictor. So right now there's only one. So because it's 0.000, it's less than 0.05, this is a significant predictor of horsepower. Oh, cool. It actually goes through it. Okay, I'll use this then. Forgot that it did that. So this is the y-intercept. So this is the expected horsepower when engine size is 0, right? So in this case, we'd never see a value this low in real life because there will never be an engine size of 0. So the idea is if the engine size is 0, that's the constant, and as you increase the engine size, you multiply it by this number and add it, and that'll give you your predicted horsepower. So this is the change in outcome associated with a 1 unit change in the predictor. So in other words, a 1 unit change in engine size is associated with a 42.99 unit increase in horsepower. So engine size is in liters. So every time you have an engine that's 1 liter bigger, the horsepower will be 42.99 horsepower higher. And that's our prediction. Okay? Here's the significance level. If this is less than 0.05, then that means that this predictor is a significant predictor of the outcome. So engine size significantly predicts horsepower. Okay? So using the model. So we'll think back to when you were a kid and in grade school and you took algebra at some point, hopefully, and you learned the equation of a line. So the equation of a line, like you learned in school, would be y equals mx plus b. M is the slope of the line, and then the b is the y-intercept. Okay? In regression, we do the exact same thing, but we move some of it around and we change the letters. So it really is exactly the same thing as 8th grade, but now we just rename it slightly and move them around. So the y-intercept moves to the front, and instead of b, it's b sub 0. Okay? That's the intercept. And then the slope moves to the back of the line. So, and it changes from m to b sub 1. And the reason for that is later we'll add more predictors, and so you'd have b sub 2, b sub 3, b sub 4, and so forth. So it's exactly the same thing, we just change the order and change the letter. Okay? We use the information from the table to fill in the equation. Okay? So I'm color coding it, hopefully that'll make life easier. So the engine size coefficient is 42.99, so that's going to go here. We call that a beta weight. And then the constant, the y-intercept, is 53.21. That's going to go here. So it's just like that. See? That came here, that came here. So there to there, there to there, just like that. The y and the x stay like that because that's what you use to get your prediction. Right? So if we know that the engine size is a certain amount, we'd multiply it by 42. So let's say it's 2 liters, right? You'd multiply that, you get something like 86, add that to 53, and then bingo, that's your predicted horsepower. Yay! Okay. So some people like to actually put the names in to make more sense out of it. So horsepower equals 53 plus 42 times engine size. If the engine size is 2 liters, you multiply these, right? Order of operations. Hopefully you went over that in your 255 and 256 classes. That's why you're supposed to learn that. So you'd multiply, then add, because it's order of operations, and that gives you a predicted value. Okay? So now, once we know the engine size of a given vehicle, we can use that to make a prediction about that vehicle's horsepower. Okay. I think I'm getting a little low on time, so I'm going to pause it here and we'll come back and do one more short video where I show you how to use that equation.